Welcome to the Radiology Advances podcast. Today we're talking about brain age, the idea that your brain has a biological age that can drift away from the number of candles on your birthday cake, and what that gap can tell us about cognitive decline.
The paper is OpenMAP-BrainAge, Generalizable and Interpretable Brain Age Predictor from MRI, published in Radiology Advances. It's by Pengyu Khan, Craig Jones, Kenichio Ishii, and colleagues from Johns Hopkins University in Baltimore in the United States.
So let's start with the core concept, because it's a lovely one. Brain age.
The idea is that you train a model to look at a brain MRI and guess the person's age. If you train it on healthy brains, it learns what normal aging looks like. Then, for a new person, you compare the brain age it predicts against their real chronological age.
And that difference is the brain age gap.
Right, the brain age gap. If your brain looks older than you are, that positive gap may signal something is accelerating the aging process, like neurodegeneration. So it's a single, intuitive number that summarizes a lot of subtle structural change.
And why do people care about boiling it down to one number? What's the clinical use?
A few things. It could help flag who's at higher risk for conditions like mild cognitive impairment and dementia, so you watch them more closely. You could track whether someone's brain aging is speeding up over time. You could even use it to enrich clinical trials by selecting people whose brains are aging faster. It's meant as a broad summary measure, not a diagnosis.
Now, people have been building these predictors for years. What's new here?
Two things the authors really care about, and they're right in the title: generalizable and interpretable. A lot of existing models work beautifully on the exact dataset they were trained on, then fall apart when you feed them scans from a different hospital or a different scanner.
Which is the classic problem with medical AI. It overfits to the quirks of one machine.
Exactly. And interpretability is the other gap. Many models give you a number with no insight into which brain regions drove it. So this team set out to build something robust across cohorts and transparent about its reasoning.
Let's get into how it's built, because the architecture is interesting. It's a transformer, not the usual convolutional network.
It is. And rather than feeding the whole three-dimensional scan in at once, which is enormously expensive computationally, they take a smarter shortcut. They sample slices from 3 viewpoints: the sagittal, coronal, and axial views, and they combine those with volume measurements from 280 brain regions.
So it's getting both the picture and the numbers, the visual slices and the actual measured volumes of each structure.
Right, and a transformer fuses all of that together. They also borrowed a trick from a model pre-trained on a huge, unrelated collection of robotics and vision data, which sounds bizarre, but that diverse pre-training seems to make it more robust to variation in how MRIs are acquired.
You mentioned combining the image views with the volume measurements. Did both actually matter, or is one just extra machinery?
Good question, and they tested exactly that. The 3 image views drove the raw accuracy, and adding the volume measurements barely moved that. But the volumes were what kept performance steady when they moved to a completely different data set. So the images give you accuracy, and the volumes give you robustness. That split is really the heart of the design.
And there's a real efficiency payoff to this design, isn't there?
A big one. Because they compress the image information cleverly, the computational cost scales linearly instead of exploding. In practice, their model ran on a tiny fraction of the computation that a standard 3-dimensional vision transformer needed, something like 50 times less, while staying just as accurate.
Let's talk accuracy. How close did it get?
On the internal test data, drawn from 2 well-known neuroimaging datasets, it predicted age to within under 4 years on average. That's competitive with the best published models.
But the headline was generalizability. So the real test is the outside data.
That's where it shines. They took an independent Australian cohort that the model had never seen, and the error barely moved. It was essentially unchanged, even a touch better. Other models they compared against degraded noticeably on that external set.
So it held its accuracy crossing into a completely new data set. That's the whole ballgame for clinical usefulness.
It is. And there was a nice detail in where the models differ. In the oldest patients, the 85 to 95 group, the competing models underestimated age fairly sharply. This model also underestimated there, but its average was noticeably closer to the mark.
Okay, accuracy on healthy brains is the foundation. But the clinically meaningful question is whether the brain age gap actually tracks disease.
And it does, very cleanly. They looked at 3 groups: cognitively normal people, people with mild cognitive impairment, and people with dementia. In a healthy group, the brain age gap sat right around 0, as it should. In mild cognitive impairment, it rose to about 2.5 years, and in dementia, it jumped to roughly 6 years.
So the gap climbs step by step with the severity of impairment. That's a really satisfying gradient.
It is, and it's exactly what you'd hope to see if the number means something biologically.
And did it separate those groups better than the other models they tested?
It was competitive. It edged out the others at telling healthy people apart from those with mild impairment, which is the hardest and most useful distinction to catch early. For the more advanced dementia cases, it was roughly comparable, actually a touch behind one competitor. So it's strongest right where early detection matters most.
Did they connect it to actual cognitive test scores, not just diagnostic labels?
They did. They compared the brain age gap against 2 standard cognitive assessments, the Mini Mental State Examination and the Montreal Cognitive Assessment. And they found a significant negative correlation. As the brain age gap went up, cognitive scores went down. Their model showed a somewhat stronger link to those scores than the competing models did.
Now the interpretability piece. This is where they try to open the black box. Which regions was the model actually looking at?
They generated attribution maps to see which structures drove the prediction. And the regions that lit up were the white matter and the deep gray matter, in particular the anterior and posterior limbs of the internal capsule, plus the caudate and the thalamus.
And that's reassuring because those regions are known to change with age.
Exactly. The internal capsule carries major white matter tracts that are known to decline in volume and integrity as we age. So the model isn't keying off some random artifact. It's focusing on biologically meaningful structures, which gives you much more confidence in the output.
Let's be careful about the limitations, though, because the authors are commendably upfront about them.
They are. First, this is a cross-sectional study. They're comparing different people at one point in time, not following individuals as they age. To really establish that a widening gap predicts decline, you need longitudinal data tracking the same brains over years.
And there's a subtlety in how they counted scans, right?
Yes. When a person had multiple scans, those were treated as independent samples, which can make the performance look slightly better than it truly is. And the cohorts skewed toward older adults and Alzheimer's-related disease. So we don't know yet how well it transfers to younger people or other neurological conditions.
One more framing point I thought was important. They're explicit that brain age gap is not a diagnostic test.
Crucially so. They stress it is not meant to diagnose Alzheimer's or any specific disease. Established tools like detailed volume analysis or fluid and PET biomarkers remain superior for actual diagnosis. Brain age gap is better understood as a broad marker of accelerated aging, a way to flag risk and monitor change.
So the honest summary is a fast, efficient, interpretable model that travels well across datasets and produces a number that meaningfully tracks cognition.
That's it. And the efficiency and generalizability are what make it realistic for actual clinical settings, where scanners and protocols vary wildly. They've also made the code openly available, which should help others build on it.
A really elegant piece of work. Thanks to Peng Yu Khan and colleagues for their work published in Radiology Advances.
If you enjoyed this episode, please rate, review, and subscribe. And you can find the full article on the Radiology Advances Journal website.
This episode was generated with the help of AI, but all content was reviewed and verified by editor Dr. Luca Solhofer from University Hospital Essen for accuracy. Thanks for joining us, and we'll see you next time.